All right, so we are going to continue our discussion of radioactive decay by finishing our cheat sheet, and we have positron emission and electron capture yet to discuss. So we're going to go ahead and fill out those last two rows, and then you guys are going to do a bunch of practice on these nuclear equations when we are done. So, positron emission, what is it? A positron is something with the mass of an electron with a +1 charge. So it's like an electron in the sense that it has the same mass, but it's opposite of an electron in the sense that it has a +1 charge as opposed to a -1 charge. So that's what it is. Its symbol is, and again, I want you to pick a marker that's going to represent positron. And so I'm going to use, I might have used this in some of your classes already, but I'm going to use green for my positron. And again, it has a 0 up top and a +1 at the bottom. So that is its symbol, and its charge is +1. It is equal in magnitude to a proton, and it is the same charge. It is equal in magnitude to an electron, but oppositely charged. Okay, we're going to wait on what happens for a second, and we're going to go on to what happens to the mass number. And in positron emission, what happens is that the mass number stays the same, because when a positron leaves, its mass is 0, its mass number is 0, so that isotope is going to have the same mass number. Its atomic number is actually going to go down by 1. And I'm going to skip over to a sample equation so we can see what happens to the neutron-proton ratio. So if I have magnesium, I want to use black for this. If I have magnesium 23 and its atomic number is 12 because that's magnesium. First I'm going to write my positron, and I want you to write that in your color. So that's E0 and +1. Now, jumping off again from where we were on Tuesday when we discussed this, and Wednesday, if you write your particle first, what remains of the isotope you can figure out. So, if the mass is 0, then the mass of my isotope must be 23, because 23 and 0 on the right have to add up to 23 on the left. Now, in order to get this part to add up, I would have to make that an 11. So an 11 + 1 on the right is going to equal the 12 on the left. And looking that up, sodium is number 11. There's one more little thing about positron emission, and that is there's always this little other guy that's released. And he kind of looks like a V with a flippy tail, and mass number 0, atomic number 0, and that is called a neutrino. Neutrino, neutrino. And neutrino means little neutral one, and a little neutral one is also emitted every time that a positron decay happens. And so it's important to show that as well. Let's look at what happens to the neutron-proton ratio. In this isotope that I start with, the neutrons, let's start with protons. Protons are 12, that's the atomic number. And the neutrons then must be 11, because 12 plus 11 makes 23. So that is something that is less than 1. Over here on this side, this isotope, the protons are 11, the neutrons are 12. Again, adding up to 23. So it's like the neutrons and protons are flip-flopping. So we go from something that is less than 1 to something that is greater than 1 to 1. And so the neutron-proton ratio in that box, we need to write, it goes up. Why does that matter? This is going to show us what kind of decay an isotope is going to want to do. So for example, if something that's radioactive has not enough neutrons, then it's going to maybe choose positron because that's going to bring the neutron-proton ratio up. So this would be a good solution to becoming more stable in that case. So if you guys look at beta, if it was too high, beta would be a good choice because it would bring the ratio down. Positron would be a good choice if we need to bring the ratio up. Okay, so that's it for positron. Nothing else we need to note, except for in the anything else, go ahead and draw your neutrino again. And so we're going to just note that it emits a neutrino, or a little neutral one, every time that this happens. Okay, and so finally, we're going to talk about electron capture. So starting off with what is it? So what is it? This is actually kind of what happens, but an electron is captured and it's brought into the nucleus. So this is the what happens portion, is that a proton and the electron turn into a neutron. So basically it's a beta particle that's absorbed instead of released. And so the symbol for this would be the same symbol as an alpha particle, but I want you to note in that box that it's written on the left. And so you can use the same color for your beta particle as you do for electron capture, or you can choose to use another color, I don't care. So a beta particle is an E with a 0 and a -1. But it's very, very important for you to note this on your chart. It's always going to be written on the left because it's a reactant now instead of a product. It's being absorbed instead of released. So that means its charge is still the same, -1. What happens is right here. This goes in the what happens. In the nucleus, a proton merges with an electron and turns into a neutron. So when I add a beta particle to my nucleus, the mass number should not change. I didn't add a proton or a neutron, I added an electron. So the mass number stays the same. The atomic number is going to go down by 1 because that proton is being sucked in with the electron, so it looks like I'm losing a proton and exchanging it for a neutron. Let's do the sample equation again first and then go back and do the ratio. So we're going to use krypton. Oops, I want to use black again. We're going to use krypton, and krypton is 36, and it'll be a mass of 86. And remember, we write that beta particle on the right-hand side, or excuse me, the left-hand side now. So that beta particle is going to be added over here before I draw my arrow. So those two combined, and if you can remember that it's a beta particle, it's just being absorbed, then it's going to automatically tell me what I get. So the mass number is going to be 86, 86 plus 0, and the atomic number is going to be 35, because 36 and a -1 make 35, and that gives me bromine. I'm sorry, this 86 should be an 81. I have terrible handwriting in my notes. So let's change that to 81. And then I also get a neutrino in electron capture. So there we go. Let's look at what happens to the neutron-proton ratio. So I start with 36 protons, and 81 minus 36 is, oh, sharp, quick math, 45. So quite a bit over 1. And then here I have 35, and 35 plus 46 And so that is going to be more than what I started with. So in summary, my ratio is coming up. I don't trust myself with that mental math, but that's right. Okay, so I get one more neutron and one less proton. So it's going to bring the ratio up. So another option, if your ratio is too low, is to undergo what's called electron capture. So what you guys are going to do next is a lot of practice of these sample equations. And so you guys are going to work through, you're going to do some alpha, beta, you're going to do some positron, and you're going to do some electron capture. And you're just going to practice writing those equations. Now don't forget that these last two that we talked about, in the anything else, we need to say emits a neutrino. And it's very important that you include that as a part of the reaction because it is something that is created and released. So make sure you're writing that. I do have a key for those practice problems, so as you are working, make sure you check the key. I will be posting it on Edmodo for you, so you can see how you're doing. That's it for now. I hope you have a lovely Friday and a fantastic rest of your weekend. See ya!